The morning of September 20th, 1944, Arracourt, France. Staff Sergeant James Barese crouched inside his Sherman tank, watching the fog swirl across the muddy fields of Lorraine. His hands gripped the turret traverse, rotating the 76mm gun left, then right, searching for movement in the mist. Behind him, the loader checked the ammunition rack. Standard M62 armor-piercing rounds. The same shells that had bounced off Panther turrets for 2 months. The same ammunition that turned firefights into death sentences at anything beyond 300 yards. Then the order came crackling through the radio headset. Load HVAP, 2,000 yards. Barese had never heard those words together before. HVAP high-velocity armor, piercing the tungsten-cored miracle round that Ordnance had promised would change everything. The round they'd been saving, the round that cost more to manufacture than a Jeep, 2,000 yards. The distance at which Panthers killed Shermans with impunity. The distance at which American tankers had learned to die without fighting back. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Something fundamental shifted in American tank warfare that September morning. Not because the Sherman suddenly became superior to the Panther. Not because American armor finally matched German specifications. The shift occurred because American tankers discovered they could fight Panthers at ranges that had previously meant certain death. This discovery, born from tungsten shortages, engineering desperation, and the systematic analysis of captured German tanks, would reshape every tank engagement from Lorraine to the Elbe River. The story of HVAP ammunition reveals a truth about warfare that specifications cannot capture. Superior technology means nothing if it arrives too late, costs too much, or cannot be produced in meaningful quantities. The Americans learned this lesson by watching their own Shermans burn. The Germans never learned it at all. July 12, 1944, Isigny-sur-Mer, Normandy. A testing range hastily prepared in captured French farmland. 3 Panthers sat as targets, vehicles abandoned by their German crews during the chaotic retreat from the Normandy beachhead. American ordnance officers had convened a board to answer a question that was killing tankers every day. Could American guns penetrate Panther armor? The answer was catastrophic. The 75mm M3 gun, mounted on the majority of Shermans landed in Normandy, could not penetrate Panther frontal armor at any range, not at 2,000 yards, not at 1,000 yards, not at point-blank range with the muzzle touching the glacis plate. The shells simply bounced off the sloped 80mm armor, leaving chalk marks where American tankers had tried and failed to fight back. The new 76mm Monet gun, the weapon that Ordnance had assured field commanders would solve the Panther problem, performed only marginally better. Using standard M62 armor-piercing capped rounds, the 76 could not defeat the Panther's glacis plate at any practical combat range. Against the turret mantlet, penetration was possible only at ranges under 100 yards. 100 yards. The distance at which German 88mm guns and 75mm KUK-42 cannons had already destroyed the Sherman 3, 4, sometimes 5 times over. The Isigny tests documented what American tankers had learned through blood and fire in the hedgerows of Normandy. The Sherman was outmatched, not by small margins that tactical skill could overcome. Outmatched by specifications so overwhelming that courage became irrelevant. A Panther could engage Shermans at 2,000 yards with reasonable expectation of first-round kills. A Sherman could not then hurt a Panther frontally until it closed to within 100 yards, exposing itself to devastating return fire for the entire approach. The mathematics were merciless. Average tank engagement range in the European theatre was 800 to 900 meters. Within this envelope, Panthers killed Shermans with mechanical efficiency. The KUK-42 gun-firing Panzergranate 3942 armor-piercing rounds could penetrate 109 millimeters of armor at 1,000 meters. Sherman frontal armor measured 76 millimeters. Vertical. No slope, no chance. General Dwight Eisenhower received the ICINI test results on July 2nd, relayed through field commanders whose tankers were dying in numbers that could not be explained by tactical errors alone. The complaints had been building since D-Day. Tankers reported shooting Panthers from the front and watching their 75mm rounds bounce off like thrown rocks. They reported Panthers firing, through morning fog, killing Shermans at ranges so extreme that American crews never saw their killers. On July 12th, Eisenhower convened a board to determine what weapons were available that could defeat the Panther. The board's conclusion, submitted after reviewing the ICINI tests, was devastating. None of the United States' standard weapons could defeat the Panther frontally at normal combat ranges. The 3-inch gun M7 mounted on M10 tank destroyers could penetrate the Panther's gun mantlet only from 200 yards. The 76mm offered nothing better. American tankers in Normandy that summer understood they were outgunned. What they did not yet understand was that American ordnance had been working on a solution since 1943, a solution that required tungsten, the strategic metal that China supplied and Germany desperately sought. A solution that would arrive in France inside wooden crates, marked top priority air transport. The technical principle behind HVAP ammunition was elegant. Instead of firing a full-caliber steel projectile, fire a sub-caliber tungsten core surrounded by a lightweight aluminum body. The aluminum sabot would give the round full-bore diameter for the gun barrel, then peel away after leaving the muzzle. The tungsten core, substantially denser and harder than steel, would continue to the target at velocities impossible for full-caliber projectiles. Tungsten carbide has a density of 15.6 grams per cubic centimeter. Steel has a density of 7.8 grams per cubic centimeter. This difference meant that a tungsten penetrator could be half the diameter of a steel penetrator while retaining similar mass. The smaller cross-section concentrated kinetic energy into a smaller impact area. The higher velocity delivered more kinetic energy overall. The result was penetration capability that exceeded full-caliber steel by enormous margins. The 76mm M93 HVAP round, standardized for production in July 1944, fired an 18.9-pound projectile containing approximately 6 pounds of tungsten carbide. Muzzle velocity was 3,400 feet per second, compared to 2,600 feet per second for the standard M62 armor-piercing round. This 800 foot per second velocity increase translated directly into penetration capability that the ICINI tests would confirm exceeded American expectations. But there was a problem. Tungsten was scarce. The United States imported tungsten primarily from China, through supply lines that Japanese conquests had severed or threatened throughout the Pacific War. Domestic tungsten production existed but could not meet wartime demand. Tungsten was required for machine tools that manufactured everything from aircraft engines to artillery shells. Tungsten was required for electrical contacts, light bulb filaments, and armor piercing, ammunition for multiple calibers. Every HVAP round fired at a Panther consumed tungsten that could have manufactured tools to build more Shermans. The strategic calculus was brutal. How much tungsten could be allocated to 76mm HVAP production when the same tungsten could produce machine tools, 3-inch HVAP for tank destroyers, or 90mm HVAP for the new M36 tank destroyers entering production? American ordnance made the decision. Priority would go to tank destroyer units. Tank destroyers were doctrinally assigned the anti-armor mission. Shermans were doctrinally assigned infantry support. Therefore, tank destroyers would receive HVAP first, in larger quantities, with sustained supply. Sherman units would receive HVAP when production permitted. If production permitted, the first 1,000 rounds of 76mm T4 HVAP, the experimental designation before standardization as M93, were produced in July 1944. They were loaded onto aircraft and flown to France for immediate testing at ICINI. The urgency reflected American desperation. The Normandy breakout was succeeding, but at a cost in Shermans that could not be sustained indefinitely. Something had to change. August 20th, 1944. The second round of ICIGNI tests. This time, the board would test the T4 HVAP against captured Panthers under controlled conditions, measuring penetration at various ranges against various parts of the Panther's armor layout. The results would determine whether tungsten could solve what steel could not. The tests used 3 Panthers as targets. Experienced American gunners fired from measured distances, recording hits, penetrations, and failures. The data accumulated with mathematical precision, numbers that would be typed into reports, transmitted to Washington, analyzed by engineers who had never seen a Panther except in photographs. Numbers that would determine whether American tankers lived or died in the autumn campaigns approaching. At 700 yards, the 76mm HVAP could penetrate the Panther's turret mantlet consistently, not the rounded early mantlet that sometimes caused ricochets, but the flat mantlet installed on later production Panthers. Consistent penetration at 700 yards compared to 100 yards for standard ammunition. This was not incremental improvement. This was transformation. At 1,000 yards, the HVAP could still penetrate the Panther's turret mantlet. 1,000 yards, the distance at which Panther commanders felt invulnerable to Sherman fire, the distance at which Panthers stalked American armor columns with impunity, the distance that HVAP turned from certain death into contestable ground. The glacis plate remained invulnerable. 80 millimeters of armor sloped at 55 degrees, providing effective thickness equivalent to 139 millimeters of vertical plate. No 76 millimeter projectile, tungsten-cored or otherwise, could reliably defeat this protection at combat ranges. The physics were unforgiving. The angle was too steep, the effective thickness too great, the distance too far. But the turret mantlet was enough. Panther crews did not know which American tanks carried HVAP. They could not distinguish at 1,000 yards between a Sherman firing standard ammunition and a Sherman firing tungsten. The uncertainty changed everything. Panthers that had previously engaged Shermans at 2,000 yards with casual confidence now faced return fire that could penetrate their turrets at ranges they had considered safe. The psychological impact exceeded the physical capability. The board completed its testing and submitted recommendations. Produce HVAP in maximum quantities. Distribute to both tank destroyers and medium tanks. Prioritize tank destroyer units but ensure Sherman units receive adequate supply. The recommendations reflected desperation poorly disguised as tactical doctrine. American tankers were dying. HVAP offered hope. Therefore, produce HVAP regardless of tungsten shortages, production challenges, or strategic allocation conflicts. Reality intervened. Tungsten carbide production was complex. The metal required specialized processing, precise metallurgy, and manufacturing techniques that could not be rapidly scaled. Initial production targets called for 43,000 rounds per month for the remainder of 1944, with 10,000 rounds per month thereafter. These targets assumed tungsten availability that did not exist and manufacturing capacity that had not been built. Production began slowly. The first 1,000 rounds shipped to France in July were air-freighted at enormous cost. The second 1,000 rounds, 3-inch caliber for Montaigne tank destroyers, followed in August. After that, HVAP ammunition travelled by ship, subject to the same 10-week transit time as all other munitions. The shipping delay meant that rounds produced in August would not reach France until October. Rounds produced in September would arrive in November. By then, autumn would be ending and the winter campaigns beginning. Tank destroyer battalions received priority, as ordnance had decreed. M18 Hellcats and M10 Wolverines, equipped with 76mm and 3-inch guns respectively, got HVAP first. Sherman battalions received what remained after tank destroyer quotas were filled. What remained was never enough. Through September, October, and November of 1944, HVAP ammunition arrived in Europe at rates below even the reduced 10,000 rounds per month target. It was not until mid-January 1945 that weekly receipts exceeded 2,000 rounds. By February 1945, the average 76mm Sherman in the European theatre had received a total of 5 HVAP rounds. 5 rounds. An acquisition rate of 1 round per month per tank. 5 rounds would not sustain a battle. 5 rounds would not even sustain a single engagement if the Sherman faced multiple Panthers. 5 rounds meant that tank commanders had to decide whether to fire their miracle ammunition or save it for a more desperate moment that might never come. 5 rounds meant that the psychological advantage of HVAP, the uncertainty German tankers felt about American capabilities, exceeded the physical advantage, because most Shermans rarely fired HVAP at all. But 5 rounds were enough at Arracourt. September 19, 1944. Combat Command A of the 4th Armoured Division held a thinly defended salient around Arracourt. Colonel Bruce Clark's tankers had been fighting for 81 days straight since landing in France. They were exhausted, under strength, and about to face 2 German Panzer brigades equipped primarily with Panther tanks. The 113th Panzer Brigade attacked from the east. The 111th Panzer Brigade attacked from the south. Together they fielded 107 Panthers and 75 Panzer IV tanks, supported by 80 assault guns. A total of 262 armoured fighting vehicles against Clark's Combat Command A, which could muster perhaps 100 Shermans, most armed with 75mm guns. The German commanders expected quick victory. Panthers outgunned Shermans. Panthers out-armoured Shermans. Panthers represented German technical superiority manifest in steel and sloped plates. The mathematics of the engagement favoured Germany by margins that seemed decisive. The Germans did not know that some American Shermans carried HVAP. They did not know that American tankers had trained specifically on how to exploit Panther vulnerabilities revealed by the Sydney tests. They did not know that American artillery doctrine, American air support, and American tactical flexibility would combine with HVAP to create a killing ground where German technical superiority became irrelevant. The fog that morning was thick, reducing visibility to a few hundred yards. German Panthers advanced blindly, lacking the reconnaissance units that proper German panzer divisions would have deployed. The rushed formation of the Panzer brigades in autumn 1944 meant inexperienced crews, inadequate training, and poor tactical coordination. These were not the veteran tankers who had fought in Russia. These were replacements thrown into Panthers with minimal instruction and ordered to attack American positions they could not see. Captain Jimmy Leach commanded B Company, 37th Tank Battalion. His Shermans waited in ambush positions carefully selected during the night. When Panthers emerged from the fog at ranges under 500 yards, Leach's tanks opened fire with everything they had. 75mm high-explosive rounds that fragmented against Panther armour but created psychological impact. 76mm HVAP rounds that punched through turret mantlets with spectacular effect, sending tungsten cores through the Panther's fighting compartment to detonate ammunition stores. The Panthers that attempted to return fire found themselves exposed on multiple flanks. American tank doctrine emphasized maneuver and mutual support. German Panthers, deployed piecemeal without adequate coordination, fought as individual vehicles rather than as coordinated platoons. The result was systematic destruction. Shermans that could not penetrate Panthers frontally maneuvered to get side shots where 40mm armour offered no protection. Panthers that turned to engage flanking Shermans exposed themselves to fire from other American tanks positioned specifically for such circumstances. By noon on September 19th, 11 Panthers had been destroyed or abandoned. By evening, the German attack had collapsed. Over the next 10 days, the pattern repeated. German Panthers attacked. American Shermans maneuvered, used terrain, called artillery, and fired HVAP when they had it. Panthers burned. By September 29th, when the Battle of Arracourt ended, Combat Command A had destroyed or forced the abandonment of approximately 200 German armoured vehicles. American losses were 25 Shermans and 7 tank destroyers. The kill ratio was not attributable to HVAP alone. American artillery had destroyed more German tanks than tank fire. American air power had interdicted German fuel supplies. immobilizing Panthers that never reached the battlefield. American tactical doctrine had exploited German mistakes with precision that reflected better training and better leadership. But HVAP had contributed something that statistics could not measure. HVAP had given American tankers hope. For the first time since landing in Normandy, American tankers could engage Panthers at medium range with reasonable expectation of scoring killing hits. This knowledge changed how tankers fought. Instead of retreating when Panthers appeared at 1,000 yards, Shermans stayed and fought. Instead of accepting death as inevitable when German armor appeared, American crews believed they could win. This psychological transformation, born from 5 rounds of HVAP per tank and test data from iSigny, shaped American armor doctrine for the remainder of the war. The German 5th Panzer Army retreated from Arracourt having learned nothing except that American numbers were overwhelming. German after-action reports did not mention HVAP. German intelligence did not analyze the new American ammunition. German tankers did not understand why their Panthers, which should have dominated Sherman tanks through sheer technical superiority, had instead burned in the mud of Lorraine. This failure to learn reflected Germany's larger strategic blindness. German military culture emphasized individual technical excellence over systemic effectiveness. If German tanks were superior, then German tanks should win. If German tanks lost, the explanation must be numbers, or fuel shortages, or crew quality, or tactical mistakes. Never systemic failure. Never the possibility that American pragmatism, accepting adequate performance that could be sustained, rather than pursuing excellent performance that could not represented superior strategic thinking. By October 1944, 76mm Shermans armed with HVAP were appearing throughout the European theatre, not in overwhelming numbers, not with abundant ammunition, but present, visible, dangerous at ranges where Panthers had previously felt invulnerable. The presence of HVAP changed German tactical calculations in ways that American intelligence analysts documented through captured orders and prisoner interrogations. German tank commanders received instructions to avoid engaging Shermans at medium range unless circumstances were favorable. Panthers were ordered to fire from ambush positions rather than from open ground where American return fire could target the turret. German tactical doctrine, which had emphasized aggressive maneuver and exploitation of superior range, shifted toward defensive positions and engagement at maximum distance. This shift handed initiative to American forces. When German armor refused to attack, American infantry and artillery advanced without armored opposition. When German armor defended from static positions, American maneuver and air power systematically reduced the defensive positions. HVAP did not win battles alone, but HVAP's psychological impact on German tactical decision-making contributed to American operational success throughout the autumn of 1944. The Battle of the Bulge in December 1944 tested HVAP under the worst possible conditions. German forces attacked through the Ardennes with 4,700 armoured fighting vehicles, including hundreds of Panthers and dozens of Tiger IIs. The attack achieved complete surprise. American units were scattered, under strength, and in many cases equipped primarily with 75mm Shermans that could not penetrate Panther armor even with HVAP, which they did not have. Yet American tank destroyer battalions equipped with M18 Hellcats and M36 Jacksons, armed with 76mm and 90mm HVAP respectively, performed with devastating effectiveness. The 610th, 743rd, and 801st Tank Destroyer battalions claimed dozens of German heavy tanks destroyed using HVAP at ranges where standard ammunition would have been useless. Lieutenant Colonel Creighton Abrams, commanding the 37th Tank Battalion, went through 7 different Sherman tanks during the war, but always commanded Shermans. At Arracourt, his battalion lost 14 Shermans while destroying 55 Panthers and Tigers. Abrams' success came from understanding what Shermans could do rather than lamenting what they could not. When Abrams had HVAP, he used it to engage Panthers at maximum effective range. When he did not have HVAP, he used terrain, maneuver, and combined arms to create situations where HVAP was not necessary. General George Patton called Abrams the world champion tank commander. The title reflected Patton's understanding that tank warfare was not about specifications. It was about combined arms, aggressive leadership, tactical flexibility, and the willingness to fight with the weapons available rather than the weapons desired. Abrams embodied this philosophy. So did thousands of other American tankers who fought Panthers in Shermans throughout the European campaign. By March 1945, 18,000 HVAP rounds had reached Europe. 42% were 76mm for Shermans and M18 Hellcats. The remainder were 3-inch Vermont tank destroyers, which were being progressively replaced by M36s with 90mm guns. Distribution remained inadequate. Sherman battalions still received only a handful of rounds per tank, but the handful was enough to force German tactical changes that American forces exploited systematically. The strategic impact of HVAP transcended its physical capabilities. HVAP demonstrated that American industrial pragmatism, accepting tungsten shortages, prioritizing tank destroyers, distributing limited quantities strategically, could counter German technical excellence. HVAP proved that adequate weapons produced in sufficient numbers and employed with superior doctrine defeated superior weapons produced in inadequate numbers and employed with inferior doctrine. This lesson shaped American defense procurement for decades. The principle that the best weapon system is the one actually available when needed, rather than the one with the most impressive specifications, became foundational to American military planning. HVAP taught this lesson through blood and tungsten in the killing fields of France. The German response to HVAP revealed the fundamental difference between American and German approaches to military technology. American engineers, confronted with tungsten shortages, accepted limited production and prioritized distribution to maximize tactical impact. German engineers, confronted with identical tungsten shortages, continued designing weapons that required tungsten in quantities Germany could not supply. German APCR ammunition Panzer Granate 4042 used tungsten cores identical in concept to American HVAP. The German 75mm KBUK-42 gun on the Panther could fire APCR with devastating effect at extended ranges. But German tungsten supplies, dependent on imports from Spain and Portugal that Allied diplomatic pressure had reduced to a trickle by 1944, meant that APCR ammunition was chronically unavailable. Panthers deployed with perhaps 5 APCR rounds per tank, sometimes fewer, often none at all. This created tactical parity where none should have existed. German Panthers with superior guns and armor, but no tungsten ammunition, faced American Shermans with inferior guns and armor, but limited tungsten ammunition. Both sides rationed miracle rounds carefully. Both sides faced identical decisions about when to fire precious HVAP or APCR versus when to save it for more desperate circumstances. The technical superiority that German propaganda celebrated became irrelevant when tungsten shortages reduced German and American tanks to firing steel projectiles that could not penetrate each other frontally. The Spanish tungsten trade had enriched Francisco Franco's regime throughout the war. Spain exported tungsten to both Germany and the Allies, playing both sides with cynical precision. By 1943, Spanish tungsten exports accounted for nearly 1% of Spanish GDP and 20% of total exports. Germany desperately needed this tungsten for armor-piercing ammunition, machine tools, and industrial production. The Allies desperately needed to deny Germany this tungsten. On January 28, 1944, the United States imposed an oil embargo on Spain, effective immediately. Secretary of State Cordell Hull stated explicitly that the embargo resulted from Spain selling tungsten to Germany, thereby contributing to their war effort. The British Foreign Secretary Anthony Eden denounced Spanish assistance to Germany in the House of Commons. The diplomatic pressure was coordinated, sustained, and backed by the implicit threat that Allied victory would remember Spanish cooperation with Germany. Franco resisted for 3 months. Spain's economy, devastated by civil war and dependent on imported oil, suffered catastrophic disruption. No tanks or armoured vehicles participated in Spain's victory parade on April 1, 1944, because fuel shortages had immobilized them completely. By May 1st, Franco capitulated. The agreement signed May 2nd, 1944 limited Spanish tungsten exports to Germany to 20 tons in May, 20 tons in June, and 40 tons monthly thereafter. These quantities were insufficient for German industrial needs. The timing was critical. By summer 1944, German tungsten supplies for ammunition production had collapsed. Panthers and Tigers deployed without APCR. German anti-tank guns received reduced allocations. German industry struggled to maintain machine tool production. The tungsten shortage that American HVAP production faced in limited form, German military production faced catastrophically. American tankers never knew that their HVAP ammunition's scarcity mirrored German APCR ammunition's complete absence. They only knew that HVAP was precious, to be conserved and used strategically. This knowledge shaped tactical doctrine in ways that American tank commanders documented in after-action reports and war diaries preserved in archives. Tank commanders ordered loaders to segregate HVAP rounds in ready racks, separate from standard ammunition. The segregation ensured that loaders would not fire HVAP accidentally during engagements with soft targets. When Panthers appeared, commanders ordered load HVAP specifically. When the tactical situation permitted firing at medium or long range against Panther turrets, commanders authorized HVAP use. When the situation required firing at closer range where standard ammunition might suffice, commanders held HVAP in reserve. This ammunition discipline reflected American armor doctrine's maturity. American tankers understood that their role was not primarily tank versus tank combat. Tanks fought infantry, destroyed fortifications, supported advances, and exploited breakthroughs. Tank versus tank combat, while dramatic and deadly, represented perhaps 20% of ammunition expenditure. The remaining 80% was high explosive and white phosphorus against personnel, buildings, and field fortifications. Therefore, possessing 5 HVAP rounds did not mean carrying only 5 useful rounds. It meant carrying 5 rounds specifically for Panthers, Tigers, and other heavily armoured targets, plus perhaps 40 rounds of high explosive for everything else. The Sherman's ammunition load reflected mission requirements rather than focusing exclusively on anti-armor capability that might never be needed. German tank ammunition doctrine differed fundamentally. Panthers carried 79 rounds for the KWK 42 gun in USF-D variants, 82 rounds in USF-G. The standard load emphasized armor-piercing ammunition, perhaps 50 to 60 rounds of Panzergranate 3942 APCBC, with the remainder split between high explosive and the rare APCR when available. This load reflected German doctrine that positioned Panthers as anti-tank weapons primarily and infantry support weapons secondarily. The doctrinal difference revealed different strategic assumptions. American doctrine assumed that tanks would spend most of their time supporting infantry against varied targets, requiring primarily high explosive ammunition with limited anti-armor capability for occasional heavy targets. German doctrine assumed that tanks' primary value was destroying enemy armor, requiring primarily armor-piercing ammunition with limited high explosive for opportunity targets. Both assumptions proved partially correct and partially wrong in the reality of sustained combat operations. American Shermans that encountered Panthers without HVAP died quickly, but represented a minority of total Sherman losses. Most Shermans were destroyed by anti-tank guns, Panzerfausts, mines, and artillery threats, against which HVAP offered no advantage. German Panthers that encountered infantry positions without adequate high explosive ammunition could not suppress machine gun nests, destroy bunkers, or reduce fortifications effectively. Their armor-heavy ammunition loads optimized them for battles that occurred less frequently than the infantry support missions they actually performed. If you find this story engaging, please take a moment to subscribe and enable notifications. post-war analysis of ammunition expenditure rates confirmed what field commanders understood instinctively. American tank battalions fired approximately 70% high explosive, 20% armor-piercing, and 10% smoke or white phosphorus overall. Individual units varied. The 13th Tank Battalion fired only 55 rounds of armor-piercing versus 19,634 rounds of high explosive between August and December 1944. This extreme ratio reflected the battalion's operational assignments, which emphasized infantry support rather than anti-armor operations. German ammunition expenditure data, less comprehensively preserved, suggested similar patterns. Panthers fired primarily high explosive in defensive operations throughout 1944 and 45. Armor-piercing ammunition was conserved for actual tank engagements, which occurred infrequently enough that many Panthers never fired their armor-piercing loads before being destroyed or abandoned. This convergence of ammunition usage patterns despite different doctrinal starting points revealed warfare's practical reality. Tanks in sustained combat operations performed varied missions against varied targets. Ammunition loads had to support this reality rather than optimized theoretical scenarios that rarely occurred. HVAP's introduction into American tank warfare represented the intersection of three factors: technical innovation, industrial capacity, and strategic resource allocation. The technical innovation was tungsten carbide penetrators, developed through systematic research into armor penetration physics. The industrial capacity was American manufacturing's ability to produce HVAP at rates insufficient for abundance, but adequate for strategic distribution. The strategic resource allocation was the decision to prioritize tank destroyers while ensuring Sherman units received enough HVAP to matter. This intersection created weapon effectiveness that exceeded the sum of its parts. HVAP's physical capability, penetrating Panther turrets at 1,000 yards, combined with its psychological impact forcing German tactical changes to produce strategic effects disproportionate to the small quantities actually fired. In combat, the French Army's post-war operations with captured Panthers provided unexpected validation of HVAP's effectiveness. France operated Panther battalions from 1946 through 1950 using captured vehicles and ammunition stocks. French tankers, conducting peacetime gunnery training, discovered that Panther armor quality varied enormously depending on production, date, and factory. Early Panthers had excellent armor that resisted penetration at ranges exceeding test predictions. Late-war Panthers had brittle armor that shattered under impact, sometimes penetrating when it should not have, other times failing catastrophically when struck in vulnerable locations. The armor quality variation explained anomalous results from the Sydney tests. Some Panthers penetrated easily, others resisted penetration stubbornly. American ordnance officers attributed the variation to shot placement or angle of impact. French metallurgical analysis revealed the truth. German armor quality had collapsed as tungsten, nickel, and molybdenum shortages forced substitutions in steel alloy composition. German steel production in 1944 reached 28.5 million tons through incorporation of conquered territories, but German access to alloying metals critical for high-quality armor had disappeared. Allied bombing of Norwegian molybdenum mines eliminated Germany's primary source. Nickel shortages forced German metallurgists to reduce nickel content from 1.7% to 0.6% in some armor plates. The result was steel that met thickness specifications but failed strength requirements under combat stress. Soviet technical trials of captured Panthers confirmed French findings. Soviet metallurgists found armor plates containing inadequate alloy percentages, producing steel prone to cracking under impact. German sources described final drives as made from low-grade steel with insufficient core strength. The Panthers that American HVAP faced in autumn 1944 were not the same quality as Panthers produced in early 1943. The armor had the same thickness, but not the same resistance. This discovery raised uncomfortable questions about HVAP's actual penetration capability against properly manufactured German armor. If late-war Panthers had degraded armor that failed under stress, did HVAP's apparent effectiveness reflect tungsten penetrator performance or German manufacturing failure? The question was debated by ballistics engineers but remained academic. American tankers fought the Panthers Germany actually produced, not the idealized Panthers German engineering could have manufactured with adequate resources. The M36 tank destroyer, entering service in September 1944, provided Americans with the 90mm gun that could penetrate Panther glacis armor frontally. The M36's 90mm M3 gun, firing 33 armor-piercing rounds, could defeat Panther frontal armor at ranges exceeding 1,000 yards. With 90mm HVAP, the M36 could penetrate Panthers at ranges limited only by accuracy and target acquisition rather than projectile performance. The M36's arrival should have solved the Panther problem completely. American doctrine assigned anti-armor missions to tank destroyers, not medium tanks. Therefore, M36's hunting Panthers, while Sherman's supported infantry represented proper combined arms integration. The doctrine worked when M36s were present in adequate numbers at the right place at the right time. Often they were not. Tank destroyer battalions were corps-level assets, assigned to divisions as needed but not organic to divisional structure. This meant that armoured divisions advancing rapidly might outrun their attached tank destroyer support. Infantry divisions under attack might lack tank destroyers because they had been assigned elsewhere. The flexibility of corps-level assignment created coordination challenges that organic divisional assets would not have faced. Shermans, as divisional organic assets, were always present. When Panthers appeared and no tank destroyers were available, Shermans fought with what they had. HVAP gave them a chance. Without HVAP, Shermans facing Panthers had to rely on maneuver, artillery support, air, power, or tactical withdrawal. With HVAP, Shermans could engage directly at medium range, buying time for reinforcements, covering retreats, or exploiting opportunities that would otherwise have been lost. The Korean War validated HVAP's design philosophy and demonstrated its longevity. Sherman tanks equipped with 76mm guns faced North Korean 34-85s in 1950. The 34-85 mounted an 85mm gun superior to the 34-76 that Germans had faced in 1941. Soviet armor doctrine, crew training, and tactical employment had evolved significantly since World War II. American tankers expected difficult fights. Instead, Shermans dominated. The M319 HVAP round, developed post-war with improved penetrator design and higher velocity from better propellant, penetrated 34-85s reliably at combat ranges. American crew training and gun optics gave Shermans first-shot advantages that Korean People's Army tankers could not overcome. The battles were one-sided victories for American armor. The Korean War performance demonstrated that HVAP's fundamental concept tungsten penetrator in lightweight carrier achieving high velocity remained valid decades after its World War II introduction. The concept would evolve into modern armor-piercing, fin-stabilized discarding sabot ammunition. But the core principle of concentrating dense penetrator mass into high-velocity subcaliber projectile endured. Israeli use of Sherman tanks armed with HVAP-type ammunition extended into the 1970s. Israeli M50 and M51 Shermans faced Soviet-supplied Arab armor, including T-54s and T-55s. These modern tanks mounted 100mm guns and heavy armor that should have rendered World War II-era Shermans obsolete. Israeli engineers compensated by mounting high-velocity guns and developing ammunition that used tungsten penetrator principles refined from American HVAP research. The Israeli Shermans succeeded because Israeli doctrine emphasized crew training, tactical flexibility, and combined arms coordination, the same factors that made American Shermans effective against Panthers. Technical specifications mattered less than systematic effectiveness. This lesson, learned by Americans fighting Panthers in 1944, remained valid for Israelis fighting T-54s in 1967. The strategic lesson from HVAP transcended tank warfare. In any domain where resources are constrained, perfect solutions are impossible, and adequate solutions must suffice. The challenge is distinguishing between adequate solutions that can be sustained and perfect solutions that cannot. American HVAP represented an adequate solution, not perfect penetration at all, ranges against all targets, but sufficient penetration at tactically relevant ranges against specific high-priority targets, produced in quantities that could be sustained despite tungsten shortages. German APCR represented pursuit of the perfect solution without adequate resource allocation. German ammunition designers created APCR with performance exceeding American HVAP. German guns fired APCR at velocities American guns could not match. German tanks that carried APCR were more capable than American tanks carrying HVAP, but German tungsten supplies could not sustain APCR production, rendering its superior performance irrelevant when German tankers fought without it. This pattern repeated throughout German military production. The Me-262 jet fighter was superior to any Allied aircraft in performance, but deployed in numbers too small to affect strategic outcomes. The Tiger II tank mounted armor impervious to any Allied gun, but broke down so frequently that operational availability never exceeded 50%. The Type XXI U-boat incorporated technologies decades ahead of Allied submarines but entered service weeks before German surrender. German engineering excellence produced weapons optimized for performance without adequate attention to producibility, sustainability, or operational integration. American engineering pragmatism produced weapons optimized for systemic effectiveness rather than individual performance. The Sherman was adequate rather than excellent. HVAP was limited rather than abundant, but adequacy sustained over time defeated excellence that could not be maintained. American tanks reached Berlin. German tanks littered the roads to Berlin, abandoned when they broke down or ran out of fuel. The human cost of these differing philosophies was measured in thousands of lives. American tankers who died in Shermans before HVAP arrived might have lived if tungsten had been more abundant, or if the 76mm gun had been deployed earlier. German tankers who died in Panthers while carrying no APCR might have lived if German industry had prioritized ammunition production over tank production. The casualties reflected strategic decisions made in Washington and Berlin by leaders who never saw the tanks burn. But the survivors' accounts reveal something that casualty statistics cannot capture. American tankers believed they could win. This belief, reinforced by HVAP's existence even in tiny quantities, shaped how American armor forces fought. German tankers increasingly believed they would lose. This belief, reinforced by fuel shortages, ammunition scarcity, and mechanical unreliability, shaped German tactical caution that handed initiative to American forces. Staff Sergeant James Barese survived the war. His Sherman was knocked out twice, once by a Panzerfaust in Belgium, once by an anti-tank gun in Germany. Neither time did he face a Panther at extended range. He fired his HVAP allocation only 3 times, scoring 1 confirmed turret penetration at 800 yards and 2 misses. The 3 rounds represented 0.0001% of total American HVAP production. Their strategic impact was immeasurable, because Barese's Panther kill was witnessed by other American tankers who understood what it meant. HVAP worked. Shermans could fight Panthers at medium range and win. This knowledge spread through tank battalions, tank companies, tank platoons. The knowledge changed tactics, boosted morale, and convinced American tankers that technical inferiority was not tactical destiny. German intelligence never conducted systematic analysis of American HVAP ammunition during the war. Captured American ammunition was examined, but no comprehensive assessment of HVAP's penetration capability, production quantities, or distribution patterns reached German tactical commanders. This intelligence failure meant German tankers continued engaging Shermans at medium range, unaware that some Shermans carried ammunition capable of killing Panthers at distances Germans considered safe. The intelligence failure reflected broader German intelligence inadequacies throughout the war. German intelligence underestimated American industrial capacity, underestimated American combined arms doctrine, and underestimated American technological innovation. These underestimations shaped German strategic decisions that proved catastrophic. By the time German intelligence recognized American capabilities accurately, Germany lacked resources to respond effectively. American intelligence, by contrast, maintained obsessive focus on German armor capabilities. Every captured Panther was measured, tested, analyzed. Every engagement report was studied for tactical lessons. Every technological development was assessed for implications. This intelligence effort informed decisions about HVAP production, 76mm deployment, M36 development, and M26 Pershing introduction. The decisions were not always optimal, but they were informed by accurate understanding of German capabilities. The asymmetry of intelligence effectiveness compounded the asymmetry of industrial capacity. American forces knew what they faced and adapted systematically. German forces fought with outdated intelligence and failed to adapt. HVAP represented one small example of this larger pattern American innovation, responding to German capabilities, while German doctrine remained static. By April 1945, American tank forces included M26 Pershing heavy tanks with 90mm guns, M36 tank destroyers with 90mm guns, 76mm Shermans with HVAP, and 75mm Shermans with improved tactics. This combined force possessed depth, flexibility, and sustained combat power that German armor forces could not match. The Panthers, Tigers, and Tiger IIs that survived were individually superior to any American tank except the Pershing, but individual superiority was meaningless against combined arms formations, supported by overwhelming artillery and air power. The final accounting of HVAP production revealed the constraints American industry faced. Total HVAP production through March 1945 was approximately 18,000 rounds for 76mm and 3-inch guns combined. 42%, roughly 7,500 rounds, were 76mm for Shermans and M18 Hellcats. Divided among hundreds of Sherman battalions, this produced the 5 rounds per tank average that defined HVAP scarcity. 18,000 rounds represented perhaps 0.1% of total American armor-piercing ammunition production for tank guns. The proportion reflected tungsten's scarcity and HVAP's specialized role. HVAP was never intended to replace standard ammunition. It was intended to supplement standard ammunition for specific high-priority targets when standard ammunition was inadequate. This supplementary role defined HVAP's success. By existing, HVAP changed German tactical behavior. By being distributed strategically, HVAP ensured that some American tanks in every sector carried capability against Panthers. By being conserved carefully, HVAP remained available when critically needed, rather than being expended against targets where standard ammunition sufficed. The Germans never achieved this balance. German APCR production, limited by tungsten shortages, was distributed primarily to elite formations. Regular Wehrmacht panzer divisions received little or no APCR. This concentration meant that some German tanks had excellent anti-armor capability, while others had none. The uneven distribution created tactical unpredictability that American intelligence exploited in Gauge Panthers aggressively, when intelligence suggested APCR was unlikely, maintained caution when facing elite formations likely to have APCR stocks. The lessons learned from HVAP influenced post-war American armor development profoundly. The M48 pattern, tank, entering service in 1952, was designed from inception to fire subcaliber ammunition with tungsten or depleted uranium penetrators. The M60 tank, entering service in 1960, continued this emphasis. The Mohn Abrams, entering service in 1980, fires exclusively sub-caliber fin-stabilized penetrators with depleted uranium cores, making the HVAP concept the standard rather than the exception. Modern American tank ammunition reflects HVAP's fundamental insight. Dense penetrator cores accelerated to high-velocity defeat armor more effectively than full-caliber projectiles, regardless of conventional armor piercing. Design optimization. The physics are immutable. The engineering challenge is manufacturing penetrators with adequate materials and achieving velocities that maximize kinetic energy transfer. American industry solved these challenges in 1944 with tungsten and aluminum. Modern industry solves them with depleted uranium and advanced sabot design. The principle endures. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.